Let's get started. Good morning, everyone. Welcome to today's ISDSA workshop titled Introduction to Graph Machine Learning. Our speaker today is Professor Jundong Li from the University of Virginia, where he holds appointment in the Department of Electrical and Computer Engineering, the Department of Computer Science, and the School of Data Science. Dr. Li's research lies at the intersection of data mining and machine learning, with a focus on graph machine learning, trustworthy and safe AI, and more recently, large language models. He has published over 150 papers in top-tier venues and has been recognized with several prestigious awards, including the 2024 KDD Rising Star Award, 2023 PAKDD Early Career Research Award, and an NSF Career Award in 2022. Today's workshop will introduce key concepts and methods in graph machine learning, an increasingly powerful paradigm for modeling relational and structured data. Now let's welcome Dr. Li to begin his presentation.
Okay, yeah. Thank you, Lingbo, for the introduction. And also thank you, I think, for the organizers for the invitation. So it's my great honor to be here to give this 3-hour tutorial or workshop about the topic of the graph machine learning. Okay, so let's get started. So nowadays, that graphs, or we also call it networks, are actually everywhere around us. So the graphs or the networks basically can be considered as a kind of the universal language to describe different kinds of data, and all, as well as characterize the relationships between different data samples. So we can see that the graphs or the networks from many different fields like the science, nature, technology, they are more similar than we can expect, right? So for this tutorial, we will use the terminology of the graphs and the networks interchangeably. Okay, so they have the same meaning. Okay, so here I give some specific examples of the graphs in our daily life. Right? So the first example is about the social networks. Right? So social networks is a big graph. So each node is a user. Right? So for example, if we use some social media platforms like Facebook, WeChat, LinkedIn, Twitter, right? So and different users that they are connected with each other through different kinds of relationships, right? So for example, two users can be the friends, right? So they can follow each other and they can also join the group together, right? They may also share some content information together, right? So different relationships can be observed. And also the size of the graph could be very huge. So this is another real-world example. It's about the World Wide Web. So the web is also considered as a huge graph, right? So here I show some detailed statistics, right? So the number of indexed web pages in the web is almost around 3.6 billion as September 1st of 2024. But if we can see this figure, right, so you can see that the number of indexed webs basically is still a small subset of the total web pages, right? Because there are many other web pages. We call it the deep web or the dark web. They are not really can be indexed by some search engines. Okay, so here that different web pages they are also connected, for example, through some hyperlinks. So this is also a huge graph. So this is another example, right? It's about the power grids, right? So each node, so this is example about the transmission grids in the United States. So each node can be a power plant or the power grid, right? So they are basically connected with each other, right? Through some high voltage power lines or the low voltage power lines. Okay. So this is another example. We call it a knowledge graphs. So knowledge graphs basically is initially invented by the Google, right? Trying to provide a way to describe the different kinds of the entities, right? So they use this kind of the knowledge graph to enhance their search engines originally. Okay, so you can see that in the knowledge graph we have different kinds of entities, and they are also connected with each other through different kinds of relations. Right? So for example, we can see that Mona Lisa is in the Louvre. Right? Louvre is a museum. Louvre is located in Paris. Right? Different kinds of relations can be observed in this graph. Okay, so this is some examples in the biology. Right? So here I show two different examples. So the first one is called the protein-protein interaction networks. Right? So each node is a protein. So basically, there are different proteins that they connected with each other. Right? So we call it the protein interactions. And the second example is called the metabolic networks. Right? So the nodes are the metabolites and enzymes, and the H's denote the biochemical interactions between different nodes. Okay, so here are some more examples like the citation networks, right? Internet of Things, financial networks, information networks, logistic networks, transportation networks, right? So the key message here is that the graphs are actually everywhere around us, right? Okay, so since graphs are everywhere, right? So so for this tutorial, so basically that we'll focus on developing some machine learning models or the algorithms to deal with this kind of graph data, right? So basically that we hope that if we explicitly model the relationships between different entities in the graph, so we hope that we can achieve better prediction performance. Okay. So then the main question we're trying to address in this tutorial is that how can we take advantage of the graph structure information, right, in order to get better prediction results. Okay. So, so here is an example about some traditional modern machine learning toolbox that we can use nowadays, right? So, for example, if we have image data, right? So, I think one standard and probably the state-of-the-art methods to deal with the image data is called a method called the convolution neural networks, right? So basically that they will stack multiple convolution and pooling layers to deal with image data, right, in order to get some representations of the image and then make use of the representations to get the predictions. Okay, so here you can see that we have three hidden layers in this convolution networks. And also, we may also have the text or the speech data, right? Text or the speech data, you can consider them as a kind of the sequential data, right? So nowadays, some popular methods to deal with the sequential data includes the recurrent neural networks. And more recently, I think some people may be familiar with the transformers, right? So they may basically take the sequential text data as input and then can perform different kinds of the tasks on the text data, right? Like the text generation, right? So, so here, what I want to say in this slide is that we can see that the modern deep learning toolbox, they are originally designed for some simple data, right? So we can consider image as a simple data because basically you can consider each pixel as a node in this grid, right? And also for the text and speech data, they basically have some specific sequential structures, okay? Okay, so then we want to develop some machine learning models on the graph data, right? But developing some machine learning models for the graph data is considered to be a quite challenging task, right? Compared with some traditional data like the image or the text. So the main reason here is that we can consider that the graphs or the networks, they actually have an arbitrary size, right? So typically you don't know how large the graph is, right? But for the, let's say for the images, right? So if you develop some convolution neural networks, basically, if we design some spatial filters, that is the spatial filters basically have a fixed size, right? And also if we take the text data as input, we may have a sliding window, which is also has a fixed size, right? But for the graph data, basically their size can be arbitrarily large. And they may also have some complex topological structures among different nodes, right? So in the other words, that we may not necessarily have the so-called spatial locality structure like the grids in the image and the text, right? So for example, if we look at this particular node in the image data, right? So basically that it has other uh, other 8 nodes around this particular node in the grid, right? But for the node in the graph, right? So it may have an arbitrary number of neighborhoods. Okay. So, and additionally, that the graphs basically the nodes or the edges in the graph may also have some feature information, right? And the graphs could also be evolving over time. So it may basically bring some additional challenges to develop some machine learning models here. Okay, so for this tutorial, so basically we try to develop some machine learning models for the graph data. We hope that the models we develop basically can deal with different kinds of prediction tasks on the graph, right? So here is a big graph, right? So here we can see that for each specific node, right, we may have some prediction tasks at the node level, right? So for example, we may do the classification for the nodes, right? And we may also basically develop some unsupervised learning algorithms, right? Trying to identify some suspicious nodes on the graph, right? So this is called a norm detection problem, right? And we may also have the age level prediction task, right? So for example, we may try to predict whether two users in a social network, right, if they will become friends with each other in the future. So this is a typical age level task. And we may also have the subgraph level task, right? So for example, we may want to group different nodes into different communities, right? So basically, we hope that the nodes in the same community that they may have some shared uh, characteristics or the preferences, right? And at last, we may also have the prediction task at the whole graph level, right? So for example, if the graph itself is, let's say, a molecular graph, right? So we may basically try to predict the properties of a molecule, right? So this is essentially a prediction task at the graph level. Okay. So here are some specific about these tasks. Right? So for example, for the node level task, right? So I think one typical task is called the node classification, right? So here an example is that we may have a citation network. Each node is a paper, right? So then different papers, they may cite with each other, right? So paper basically are from different areas, right? We may have a paper from some computer science venues or from some psychology venues, right? And ages denote the citations between different papers, right? So in this graph that we know that some nodes we already have their specific class labels. Right? So for example, we know which area this paper belongs to, right? But there are some other nodes we don't know their labels, right? So here, our goal is that we're trying to ensure that the model can predict the missing labels for these unlabeled nodes. And this is a norm detection task, right? So this is more like, as I mentioned, it's more like an unsupervised task, right? Different, let's say we have the social platforms, right? So we may have the connections among the users, right? So we may try to develop some learning models that can identify some suspicious or the malicious users, right? Okay, so this is an edge level task, right? So I think one typical problem is called the recommender systems, right? So basically, for the recommender systems, we have a bunch of users and we have a bunch of items. For example, the items can be the movies that the user has watched before, right? So we have the historical interactions between the users and the movies, right? And based on the user's preferences, based on what movies that they have watched previously, so we may try to predict some interesting movies that the user might like in the future, right? So essentially, this is kind of the link prediction or the age level link prediction task. We're trying to predict whether there will exist these ages in the future. Okay. And this is another age level task. It's basically a problem in the biology or the medicine. It's called the drug side effect prediction, right? So here that in this graph, the nodes are the drugs and the proteins, right? So we have two different type of nodes. So the green ones denote the drugs and the orange ones denote the proteins. right? And we may have the drug protein interactions, right? Basically, which specific protein structure that the drug has, right? And we may also have the protein-protein interactions, okay? And also we have some existing knowledge about, let's say when patients take some specific medicines together, it may have some side effects, okay? And here, an important task is that we're trying to predict some potential side effects, right? So let's say, because the knowledge we have about the side effects could be very limited, right? So we may leverage some machine learning models to predict whether whether potential side effects will happen between two drugs in the future. Okay, so this is also edge level task. And this is also a knowledge graph completion, right? So as we mentioned that we may already have different kinds of relations among entities in a knowledge graph, right? But the knowledge graph could be incomplete, right? So we may try to find some ways to basically refine the knowledge graph to make it to be more complete, right? So essentially, this is a edge level prediction task. Okay. And also for the subgraph level task, right? So here we can see that an example is about the social networks, right? We're trying to do the so-called community detection in a social media. So the nodes are the users and edges are the user-user connections. And we're trying to develop some unsupervised methods to detect the community structure in the network, right? The community essentially is a kind of we call it the clustering on the graphs, right? We're trying to find the best partition of the nodes, right? So in a way that we can partition the graphs into different parts. Okay, and this is another example about the missing information detection, right? So basically, when users post some tweets in Twitter, right? So basically, that the tweet basically will be retweeted by many other users. Okay, so for each tweet, if you look at the propagation structure, so each propagation structure you can consider it as a kind of the tree structure, right? The root node is a tweet, and we have many different users, right? And people find that basically compared with some uh, true information, the missing information basically has some specific cascading structures, right? So basically that they can make use of the machine learning models to better understand uh, the, the tree structure in order to identify whether the original tweets is misinformation or not. And this is a graph level task, right? So this is a problem called the network alignment, right? So for example, that the users basically, they may have different social media platforms, right? So for example, a user may basically join the WeChat. It may also have the Facebook and the Flickr account, right? But the different platforms, they don't talk with each other, right? So, so if we want to provide some better service to the users, so one way we can do is that we can try to identify the same user across different platforms, right? So in this specific task, we're trying to solve this kind of problem through the network alignment problem, right? So for example, we can see that this specific user has an account in the network one and the network two, right? Okay, so this is another graph level task. It's about the drug discovery. So the nodes are the atoms and the edges are the chemical bonds between the atoms, right? So we know some specific properties of the drugs, right? And then we're trying to develop some models that can help us to predict some promising molecules from a pool of candidates, right? So in this way that it can significantly reduce the cost for the drug repurposing and the new drug discovery. So and also there are many other applications for the due to the time limit, don't plan to go through all of them, right? So like the traffic prediction, weather forecasting, some mental disorder analysis, right? Visual marketing, and the software dependency analysis. Okay, So this is basically a brief introduction about what we want to do for the graph machine learning. And for this tutorial, I try to break the whole content into four parts. For the first part, I want to talk about some classical methods, right, to learn some representations for the nodes in the graph. So we call it node embeddings. And after that, I will spend some time to talk about some deep learning models on the graph. It's called the one popular method is called the graph neural networks or the GNNs. And after that, we will have a short break. And after the break, I will also cover some advanced topics on the graph neural networks, including can we provide a general framework for the GNN model. So in this way that you can also try to develop your own GNN models by yourself. And also we will talk about how can we uh, train a GNN model, right? How can we do some data augmentation and facilitate the training. Okay. Okay, so let's go to the first part about the node embeddings. So for the traditional machine learning, right? So we can see that if the input data is a graph, right? So if we want to develop some machine learning models, so the traditional strategy is that we can try to extract some node, link, or the graph level features, right? So basically, it's called the feature engineering. And then after we have some features, right? So basically we can feed the features into some standard learning models like the support vector machine, neural networks, decision tree, right? So then we can map the features to some specific prediction labels, right? So this is a very traditional pipeline of the machine learning, right? But we can see that one limitation here for the traditional machine learning pipeline is that it requires the feature engineering process every single time, right? Every time you have a new feature, a new graph, you may actually extract some feature information from the graph, right? And then apply the downstream prediction tasks, right? So so what are we trying to do here is that we're trying to develop some machine learning models that can automatically help us to learn some good representations for the graph. So in this way that we can avoid the labor-intensive feature engineering process. Okay. So this is called the graph representation learning, right? So the goal here is that we're trying to develop some efficient, task-independent feature learning methods in order to map each node in the graph to some feature representations, right? So this feature representation is essentially is a vector, right? It's a d-dimensional vector for each node, right? So the input is a graph, and then we're trying to map each node into a vector, right? So after we get the vector representation for all the nodes, then we can apply any downstream models. So that's why it's called the task independent, right? So this kind of the mapping process is independent of any downstream tasks. So we don't care whether the downstream task is node level task, graph level task, or the edge level task. Okay. So essentially, as we mentioned, the task is that we want to map the nodes in the graph into a vector, or we also call it an embedding space, right? So these vectors are also called the embeddings. So the basic idea is that we hope that the similarity of the embeddings between the nodes can indicate their similarity in the original graph, right? So for example, if we two nodes are close to each other in the original graph, we hope that after this kind of mapping, right? So the embeddings for these two nodes are still close to each other in the Euclidean space, right? So essentially, we're trying to find a way to encode the graph or the network information, right? So the vector representations can be potentially used for many downstream prediction tasks. Okay, so this is an example about a classical example. This is called the Zachary's Karate Club network, right? So you can see that the input is essentially a graph, right? We have probably around 30 nodes. And after the mapping, we map each node to a two-dimensional vector, right? So basically that this is where these different nodes locate in this two dimensional space, right? So we hope that if two nodes, they are already connected with each other in the original graph, they should also be close to each other in the embedding space. Okay. So this is the problem setup. I noticed some questions in the chat. Yeah, I will explain this question later. Okay, so I think this is for this slide. So the input is a graph, right? So V is the node set, or we also call it the vertex set. E is the edge set. A basically is a matrix. We call it the adjacency matrix, right? So basically, you can see that for this graph, we can write down the adjacency matrix for this graph. Okay, so if the entry is 1, it means that the two nodes are connected with each other. If the entry is 0, it means that the two nodes, they are not connected with each other. Okay, and for the sake of the simplicity, we assume that the adjacency matrix is binary, right? So it only has 0 and 1 entry. And also for the simplicity, for now, we consider that we only have the graph information. So we don't have any additional information for the nodes or edges, okay? And the basic goal here is that we're trying to uh, find some encoding function, or we also call it encoders, right, to map different nodes into a vector, right? So ZU and ZV are vectors in the embedding space, right? So the basic goal is that we hope that the similarity of two nodes in the embedding space, right, can well approximate the similarity in the original graph, right? So in the other words, let's say if these two nodes, U and V, they are similar with each other, right? In the original graph, so ZU and ZV, they should also be similar with each other in the embedding space. Okay, so then the question here is that how can we characterize the similarity of two vectors in the embedding space, right? So here we can consider that if ZU and ZV, they are both normalized vector, right? So then basically, if both of them are normalized, we can basically make use of the dot product between these two vectors as their similarity, right? So essentially that the dot product basically measures that the cosine distance between two vectors, right? Because both vectors are normalized. So the dot product is the cosine similarity. Okay, so then we already define how can we measure the similarity of two nodes in the embedding space, right? So then the next question we're trying to answer is that how can we define this kind of the mapping function or the encoding function, right? So this is a general pipeline for to learn the representations for the nodes, right? So first we need to define an encoder or encoding function. We also call it encoding. Right? Encoding basically is a mapping from the nodes to the embeddings. And we also need to define a node similarity function, right? Because we hope that the dot product of the two nodes in the embedding space can well approximate the similarity of the nodes in the original graph. We need to define a node similarity function in the original network, right? And we also need to define a decoder, right? So that can map from the embeddings to the similarity scope, right? So more specifically, in this example, we consider that the decoder function is essentially the dot product. Okay, it's dot product, right? And here that our goal is that we want to optimize the function parameters of the encoders, right? Because the decoders, we only consider the similarity, the cosine similarity. We only have the parameters for the encoders, right? So we're trying to optimize the parameters of the encoders in a way that the dot product of two vectors can well approximate the similarity. Okay. So here that there are two essential components, right? So the encoder basically is a function, right, that map each node into a node dimensional vector. So typically we consider that the node embeddings are in a node dimensional feature space. Okay. So then we also need to define the similarity function, right? So similarity function specifies how relations in the vector space map to the relations in the original graph, right? Okay. So then the question here is that how can we define the encoding function? So the most straightforward method is called the shallow encoding. Okay. So for the shallow encoding, So the encoder is just an embedding lookup function. Okay, what does it mean? It means that we're trying to learn a vector orientation for each node, right? So if we concatenate all the nodes together, essentially we're trying to have a embedding matrix, right? So in this embedding matrix, each column denotes a node embedding. Okay, so this is essentially what we're trying to learn, right? And if we know this kind of the embedding matrix, right? So if we want to get the embedding for a specific node, what should we do? We just extract the corresponding node in this matrix, right? So then we also multiply it with indicator vector v. V is the indicator vector, right? So for this vector, all the entries are zero, except entry of one, right? So this is the illustration, right? So this is the embedding matrix for all the nodes. So each column denotes a vector for a specific node, right? So if we want to get the embedding for a specific node, we just take that specific column, okay? So in the other words, that each node will be assigned with a unique embedding vector, right? And our goal here is that we're trying to directly optimize the embeddings for each node. So for this kind of methods, that there are many popular methods in this direction. So I will talk about some popular methods like the deep work or the node-to-vec. Okay, so let's have a summary about the node embedding framework, right? So for the node embedding framework, so essentially it's a kind of the encoder plus the decoder framework, right? So and here that for now, we just consider we have a shallow encoder. So the encoder is essentially an embedding lookup table, right? So we're trying to learn a big matrix, right? And the matrix Z contains the embeddings for all the nodes, right? If we want to get a specific embedding for a specific node, we just take that a specific column, right? So later on that we will also cover some encoders based on some deep neural networks, right? So this is called the graph neural networks, right? And and also for the decoder, for now we just the decoder are based on the node similarity, right? Our objective is that we're trying to uh, maximize the dot product for two nodes, for the node pairs that are already similar with each other in the original graph. Okay. So then, based on this kind of the framework, then the key question we're trying to address is how to uh, define the node similarity function. Right? So the key distinction between different shallow methods here is that how they define the node similarity function. Right? So for example, we have different ways to decide whether two nodes should be similar with each other. Right? So for example, we can decide that if two nodes that they are directly connected with each other with edge, these two nodes should be connected, should be similar with each other. Right? Or in the second case, let's say if two nodes have many shared neighbors, right? So they are not necessarily connected with each other, but if they share many neighbors, we can also consider them to be similar with each other. Or if two nodes that they are not necessarily share some neighbors, but they are in the same community, we may also consider them to be similar with each other, right? Or in the other case, let's say if two nodes that they have some structural roles, similar structural roles, so they can also be considered with similar with each other. So we'll talk about different strategies later. Okay. So more specifically that we'll talk about three different ways to define the node similarity. So the first way is called the adjacency-based similarity, and the second strategy is called the multi-hop similarity, and the third strategy is called the random walk approach. Okay, so let's talk about the adjacency-based similarity. Okay, so so here that the basic idea for this kind of the methods is that the similarity function between two nodes is just the edge weight between two nodes in the original graph, right? So let's say if two nodes that they basically have a large edge weight, so we consider that these two nodes are very similar with each other. Okay. So then this is the basic optimization problem we can solve in order to learn the node embeddings, right? So we can see that the AUV denote the weight between two edges, right? So then we're trying to ensure that the dot product of these two embeddings basically can well approximate the edge weight, right? We're trying to minimize the L2 norm difference between these two um, between the ground truth and the predictions, right? And also we're trying to go through all the node pairs, right? So then we have the loss function. So this is a loss function we're trying to minimize. So after we minimize this function, we can get the embeddings for all the nodes. Okay. Um, so in order to solve this kind of the optimization problem, right, we can see that the parameters we're trying to solve is a vector for each node, right? If we concatenate them together, this is essentially an embedding matrix. So to solve this optimization problem, that is the first option is that we can use some optimization techniques, such as a stochastic gradient descent, right, as a general optimization method. So one advantage for this kind of method is that this kind of the optimization strategy, like the SGD, they are highly scalable, right? It can be very general approach, right? And the second option is that we can solve this kind of problem through some matrix decomposition solvers, right? So for example, we can use SVD or the QR decomposition, right? But if we use these matrix decomposition solvers, they can only work in some specific cases. So they are not considered to be a general solver. Okay. Although this kind of strategy is pretty simple, right? We're just trying to approximate the edge weight. There are still some limitations for this kind of the method. So one major limitation here is that if you look at this loss function, we actually need to go through all the possible node pairs, right? So the time complexity basically is quadratic to the number of nodes in the graph, right? So if the number of nodes in the graph is very large, then the quadratic complexity is considered to be not scalable. Okay. Sometimes that we can accelerate this kind of process by only just summing over the non-zero edges. Right. So we can just just sum through the observed edges. So in this way, we can reduce the complexity to the number of edges, which is linear to the number of edges in the graph. Mm. And another limitation here is that the number of parameters we're trying to uh, learn, right, basically is linear to the number of nodes. Basically, we have a vector for each node, right? So then if the number of nodes is very large, then the number of parameters we're trying to estimate will be very huge, okay? And another challenge here is that this method only considers the direct or the local connections, right? So we only consider that the two nodes are connected if they are similar with each other, right? But there are some other situations. So in this graph, we can see that the blue node, right, is obviously more similar to the green node compared with the red node, right? Although that they don't have any connections. But if we rely on this method, they cannot basically capture this kind of the relative difference between these two different pairs. Okay. So this is for the adjacency-based similarity. So we also want to talk about another strategy called the multi-hop similarity. So the basic idea for the multi-hop similarity is that we're trying to expand uh, the neighborhood for each node, right? So previously for the adjacency-based similarity, we only consider the one-hop neighbors, right? So if two nodes are connected, we consider them to be similar to each other. But here that we can consider that we can generalize the neighborhood, right? So for this red node, the green nodes are the one-hop neighbors, and the blue nodes are the two-hop neighbors, and the purple nodes are the three-hop neighbors, right? So we can consider the until the k-hop neighbors. So this is the basic idea. We also have an optimization framework, right? So here we can see that in addition to use the adjacency matrix A, so we can also make use of the A to the power of K, right? So A to the power of K basically considers the k-hop neighbors, okay? So one popular method in this family is called the graph wrap. So this is a very popular method proposed in 2015. So for this method, they actually make some modifications for the a to the power of k. So basically, they design this kind of the matrix. So they found that this kind of the log transform, the probabilistic adjacency matrix, basically is more powerful. But essentially, that you can consider this matrix basically capture the k-hop neighbors. Okay. And after that, for each case, they basically solve this problem. And they get an embedding for each node for different k, right? And after that, they concatenate all these vectors together to get a big vector for all the nodes. Okay. And additionally that we can also measure the overlap between the node neighbors, right? So for example, that for this blue node and the red node, they are not necessarily connected with each other. But here that we can look at their shared neighborhood, right? So some specific functions that can measure the shared neighborhood is called the Jacob similarity or the Adamic ADA score. Okay. And here that we can see that we replace the matrix A to the another matrix S, right? So this matrix basically can measure the shared neighborhood between any two nodes in the graph, right? So instead, basically approximate the A, we try to approximate the S, right? So in this way, that the vector that we trying to learn can capture the shared neighborhood structure. So this method is called the HOPE. Okay. So as a summary that so far we basically just define the node similarity, right? Uh, Based on the pairwise node similarities. And we're trying to optimize the node dimensional embeddings, trying to approximate these pairwise similarities, right? So the issue here is that this kind of method could be very expensive, right? Since we need to iterate over all the pairs of nodes. And also, another limitation here is that we need to hand design some deterministic node similarity measures, right? And additionally, the number of parameters we're trying to estimate could be very large, okay? And then to address this limitation, people actually come up with some other methods. It's called the random walk-based approach. So I'm not quite sure how many of you are familiar with random walk. So here is a brief introduction. Okay. So given a graph like this and a starting node, right? So basically the random walk here is that for this node, we randomly select a neighbor of this node, right? So for example, we select this neighbor and then we take a path to this particular node. And then at this node, we also randomly select another neighbor. So let's say we select 8. So we make another step toward the 8, right? And then we select a neighbor of node 8 randomly, right? So for example, node 9. So we move toward 9, and then we basically continue the process, right, until let's say we reach the path of the specific length. So this kind of the path, right, is called the random walk. Okay. So basically, the random walk is basically a sequential of points visited randomly on a graph. Okay. So the basic idea for the random walk-based embedding is that we trying to ensure that the total product of two vectors can approximate the probability that two nodes co-occur together on a random walk over the network, right? So here that we use the probability two nodes co-occur with each other on a random walk as the similarity metric, okay? So this is the basic workflow for this kind of the random walk-based embedding methods, right? So here that the first step is that we're trying to estimate the probability of, let's say we start from the node U, right? So we're trying to estimate the probability of visiting node V on a random walk starting from the node U, right? Using some specific random walk strategy R, right? Let's call R to be the random walk strategy. And then if we can estimate this kind of the conditional probability, right? So then we're trying to optimize the embeddings between two vectors, right? To ensure that their dot product can well approximate this conditional probability. Okay. So why we choose the random walk? So I think one major advantage of the random walk here is that it's because this kind of methods has a high expressiveness. So basically, random walk provide a flexible stochastic definition of the nodal similarity, right? Because the walk length can be basically it's a parameter we can decide, right? So we can basically choose a very long random walk, and we can also choose a very short random walk. So basically, that this kind of the random walk can incorporate both the local and high order neighborhood information in the graph. Okay. And the idea here is that if random walk starting from the node U visit node V with high probability, right? Then basically we consider these two nodes are similar with each other. So in this way that we can see that this kind of methods can consider the high order multi-hop information. And another advantage is about the efficiency because we do not need to consider all the node pairs when the training, right? We just need to consider the pairs that co-occur together on the random walks, right? So this is the detailed optimization procedure, right? So in the first step, we can just run some short fixed length random walks starting from each node U using some strategy R. So typically here that we use some fixed length random walk, okay? And for each node U, so we connect a multi-set NRU. So this multi-set basically denotes the nodes that are visited on a random walk starting from a node U, okay? And then we try to optimize the embeddings according to this function, right? So if we look at this function, basically we have a specific starting point U, right? And then we connect all the node V in the multi-set, and then we try to minimize this log likelihood, right? So basically, if we minimize this function, essentially it is trying to maximize this conditional probability. So in the other words, that we're trying to ensure that if we start from the node U, that the conditional probability of node V that appear in the random walk, this conditional probability should be maximized. Okay. So this is the optimization function. And then we can see that the intuition for this optimization function is that we're trying to optimize the embeddings to maximize the likelihood of the random walk co-occurrence, right? So then the key question here is that how can we formulate this conditional probability, right? If we start from the node U, what is the probability that we will reach out to the specific node V, right? So here that in order to characterize this conditional probability, we can make use of the softmax function, right? So basically that this is the formulation of the softmax function. For the denominator, we actually need to go through all the nodes, right, to get a normalization factor, okay? So this is exponential function. And then if we replace this conditional probability using this kind of the softmax function, so this is the optimization problem we're trying to solve, right? So if we optimize this function, right, basically that we can get the embedding vector for all the nodes, right? Okay. But there are still some problems, right? So if we take another look at this function, right? So basically for this summation, we go through all the nodes, right? And then we look at this softmax function. For the denominator, we also need to go through all the nodes, right? So basically we can see that this kind of nested sum over all the nodes will still give us a complexity that is quadratic to the number of nodes, right? So in the other words, that this kind of methods is still not scalable and is also computational expensive. So what should we do, right? So it seems that the normalization term from the softmax function is a bottleneck, right? So then the question here is that can we approximate this kind of the softmax function? So then people actually come up with some solutions called the negative sampling, right? So instead of just get the exact computation of the log of the softmax function, So they basically trying to come up with some clever ideas. It's called the negative sampling, right? So here you can see that this term basically can be approximated through the difference between these two terms, right? For the first term, right, we're still trying to measure the similarity between the node V, U and V, right? And then we have a function, it's a sigmoid function. And then for the second term, right? So instead of going through all the nodes, we just go through k different nodes, right? So these k nodes basically are randomly selected from a random distribution of all the nodes, right? So basically that the basic idea is that these random nodes, so the things that they are randomly selected, so we consider that they should be different from the node U, right? Because node V basically appear in the same random walk. But for these randomly selected nodes, since they are randomly selected, they should not be very similar to the node U. So we're trying to minimize, right? So their similarity, okay? So this is called the negative sampling, right? So through this kind of strategy, we can see that for the second term, we only need to select k different nodes, right? So it allows us to provide a quicker computation for the softmax function. Okay. So then the question here is that how should we, what kind of distribution should we choose, right, in order to select these k negative samples? So basically, one simple idea is that we can basically sample the negative nodes proportional to the node degree, right? So let's say if a node has a high degree, then it has a high probability to be selected as a negative sample. Okay. And the people has done a lot of studies about the negative sampling, and they actually find some specific rule of thumb to decide the k. So they find that if k is specified as a very high value, so then this kind of approximation will be very accurate, and it will provide a robust estimation of the softmax function, right? But meanwhile, it will also lead to a high computation cost. And they also find that typically if k is specified as a relatively small number, right, like 5 to 20, it already can provide a quite a good performance. So that's why if you look at some literature, you will find that k typically is specified as a number of 5. Okay. Okay, so let's take a one step back, right? So we look at this function, the whole procedure, right? We first run some fixed length random walk from each node, and then we collect the neighborhood multi-set, right, for each starting from each node, and then we try to optimize embedding according to this function, right? And then in order to approximate this function, we can use a negative sampling. Okay. So then the question here is that how should we perform the random walk, right? So since in the previous slide that we actually need to perform the random walk according to a specific strategy R, okay? So the simplest strategy is that we can just run some fixed length, unbiased random walk, starting from each node. Right? As we mentioned previously, which basically starting from each node, we can randomly select its neighbor to make the random walk, right? And then we fix the size of the length of the random walk, right? So this simple strategy actually leads to a method that is called the deep work. So this is actually one of the seminal work in the node embedding. It's published in the KDD conference in 2014. But later on, people may wonder that can we design some better strategies in order to learn better node embeddings? So in the other words, that they trying to find some better random walk strategy. So and then it comes to the second method is called the node-to-vec. So the essential idea for the node-to-vec is that they propose a kind of the biased random walk strategy. Okay, so for this random walk, right? So it called the biased random walk. So this method basically can achieve a trade-off between the local and the global views of the network, right? So let's say if we start from a node U, right? So if we only try to explore the neighbors of the node U, right? So basically S1, S2, and S3 are the direct neighbors of node U. So this is more like we perform the breadth first search. We're trying to explore the neighbors as far as possible, right? And then if we look at this random walk, S4, S5, and S6, right? So it's more correspond to another kind of the search strategy called the depth first search, right? So we're trying to go as deep as possible, right? So through the depth first search, we can try to reach out to the nodes that are multiple hops away from the center node. Okay, so so let's take another look at this figure, right? So if we choose the breadth first search, right? So we will explore the S1, S2, S3, right? So they actually are more likely to provide a local microscopic view of the node U, right? But if we choose the depth first search, S4, S5, and S6, so basically that it can provide a global scopic view of the node U, right? So this is another illustration of the difference between the BFS and the DFS. Okay, so then the basic idea for the node2vec is that they actually come up with a biased random walk strategy, right? So given a node U, it will generate a neighborhood NRU. So basically, this kind of the biased random walk basically has two specific parameters. It is controlled by two parameters. These are tunable parameters. So the first parameter is called the return parameter, right? It's P. Basically, this parameter will control how likely, right, will return back to the previous visited node, right? Basically, by tuning this parameter, basically we can control how likely that the node will perform the BFS. Okay, and another parameter we call it the in-out parameter Q. Okay, so this by tuning this parameter, we can control that whether we should moving outwards versus inwards from the previous node. So in the other words, that by tuning the parameter Q, it is more like a control the ratio of the breadth first search and the depth first search. Okay, so next we will specify how a single step of bias random walk is performed. Okay, and after that, this kind of the bias random walk strategy is just a sequence of these steps. So we just look at one single step. So this is one step of this kind of the bias random walk strategy, right? So more specifically, we're trying to specify the walk transition probability on the edges adjacent to the current node W, right? So let's say we start from the node U, okay? So the random walk starts from node U, and it traversed the edge, just traversed the edge T and W, okay? So now it has at the node W. So it should not be T. I think it should be S1. Yeah, so I think there's typo here. So let's say right now we arrived at the node W. Okay. So then we're trying to specify some edge transition probability out of the node W, right? So right now at the node W, basically we have three options, right? So basically it has three different kinds of neighbors, right? So if we choose the neighbor S1, right? So basically that it will be more close to where we start, right? So this is essentially node U. But if we choose the S2, right? Basically S2 actually has the same distance to the where we started, right? So this is the U, right? And also if we choose S3, basically we will make the path to be as far as possible from the node U, right? So the essential idea for this bias random walk is that we basically trying to remember where that walk came from, okay? So more specifically, we can see that when we arrive at the node W, right? So we actually have the parameter P and Q to control the probability that whether we should return to the node that are more close to the node U, or whether we should choose another node that is at the same distance as node U, or we choose other nodes that are further away from the node U. So these two, the weight of these edges are controlled by the P and the Q, right? So P is considered as a return parameter, right? So if P is specified as a very small number, so then this edge weight will be very high. So more likely that we will return back to the node U. But if we choose the Q to be a very small number, this edge weight will be very high. So more likely we will move far away from the node U. Okay. So far 1 over P, 1 over Q, and 1, they are unnormalized probabilities, right? But typically that we need to normalize these probabilities. Okay. So as we mentioned that if we have a lower value of the P, so we are more likely to perform the breadth first search, right? But if we choose a small number of Q, more likely we are performing the depth first search. Okay. Okay. So this is some examples, right? So let's say we choose P to be a relatively small number. So basically we have a microscopic view of the neighborhood structure, right? So in this case, if we choose Q as a relatively small number, so basically we have a global view of the network. Okay. So this is based on this kind of the random walk strategy. So this method is called the no-to-vec, right? But in addition to that, we also have some other different kinds of the biased random walk strategy, right? So for example, we can perform the random walk based on the node attributes, right? And we can also perform the random walk based on the learned edge weight, right? And also some other methods perform the alternative optimization. So they're trying to directly optimize the one hop and the two hop random walk probabilities. This method is also a very popular work called the line. And there are some other network pre-processing techniques. So for example, we can perform the random walk on the modified versions of the original network. Okay. Okay, so as a summary, right? So far, we basically talk about some methods that can embed the nodes in a way that the distance in the embedding space can reflect the node similarity in the original network, right? So we talk about the three different kinds of methods directly based on the adjacency matrix and also based on the multi-hop similarity. And later on, we also talk about some modern methods based on the random walk. Okay. So then the question here is that which method typically should we choose? So the short answer is that no one method will win in all cases, right? So people found that the node-to-vec performs better on the node classification task, while the multi-hop methods basically performs better on the link prediction problem, right? But in general, I think compared with some other methods, random walk-based methods, they are generally more efficient, right? So the complexity basically is linear to the number of edges, right? So in general, we must choose some specific definition of the node similarity that matches your application, right? So if you're in your application that if the node similarity is better to consider the multi-hop neighbors, right? So then we may choose the random walk-based methods, right? So in some application, if the one hop neighbors is sufficient enough, we can basically use adjacency-based similarity. Okay. So this is about the node embeddings. Then we're trying to generalize node embeddings to the embedding for the entire graph, right? So in many cases, as we mentioned previously, let's say we're trying to learn an embedding for a whole molecular graph. Right? Each node is atom, and we have different chemical compounds between the atoms, right? So we're trying to find the embedding for the whole graph, right? So for example, if we get the embedding for the whole graph, right, we can develop some classification models to classify the toxic or non-toxic molecules, right? We can also develop some methods to identify the anomalous graphs, right, versus the normal graph. So how can we get the embedding for the whole graph? So here we want to introduce two simple strategies, okay? So one simple strategy is that we can basically run a standard node embedding method on a graph, right? And then we try to just do the summation, or then do the average of the node embeddings in the graph, right? So here that we do the average summation of all the nodes in embeddings of all the nodes in the graph, and we consider the summation as the embedding for the whole graph. Okay. So this method is used by this paper to classify the molecules based on the graph structure. And another strategy here is that we can introduce some virtual nodes, right? So this is the example. So let's say we're trying to get the embedding for this specific subgraph. We can introduce a virtual node. So this virtual node will connect to all the nodes in this graph, right? And then we can basically run the graph embedding over this new graph, including this virtual node and the virtual connections. And then we consider the embeddings for this virtual node as the embedding for the whole subgraph. Okay. Okay, so here as a summary that we discussed two different ideas for the graph embedding, right? So the first approach is that we can embed the nodes and then we can do the summation or the average. And the second strategy is that we can create some super nodes that expands a subgraph and then we can embed that node. Okay. Okay. I think I probably should skip this part. Okay, so I will directly move to the second part is about the, so I have some additional content about the connections between the matrix factorization and the node embedding, but due to time limit, I think it's better to skip them right now, okay? I will later on, I will put the slides online, so you can, if you are interested, you can also take a look at the this content. Okay, so the second part is about the graph neural networks or the GNN models. Okay, so let's take a recap. Right, for the node embedding, our idea is that we're trying to map each node to a d-dimensional embedding space. Right, so then we can basically perform some classification tasks or some other tasks based on the node embeddings. Right. So the key question here is that how can we learn the mapping function f or the encoding function f, right? So for the node embeddings we introduced so far, so the essential idea is that we're trying to do the embedding lookup, right? So we have a big embedding matrix, and then the embedding vector for each node is basically a column in the matrix, right? So all these entries are the parameters we're trying to optimize. So, but this kind of methods has some limitations, right? So the number of parameters we're trying to estimate is linear to the number of nodes, and there is no shared parameters between different nodes, right? So the parameters for different nodes are quite different. Okay, each node has a unique embedding, and and also another limitation for this kind of method is that this kind of methods are inherently called the transductive. So the transductive means that it cannot generate for the nodes that are not seen during the training, right? So if we have some news join the graph later, so basically we have to rerun the model from scratch, right? So we can not train the model and directly generate the embedding for the new nodes. And another limitation here is that these methods we introduced so far, they only consider the graph structure. They cannot incorporate additional feature information for the nodes. Right? In many situations, we may also have some additional information for the nodes or the edges. So these are also the important information probably we should consider. Okay. So then we try to move from the shallow encoding to the deep encoding, right? So more specifically, we'll discuss the deeper methods based on the graph neural networks. So here that the encoding function or the mapping function basically is a multi-layers of the nonlinear transformation of the graph structure, right? So because this is a multiple layers of the nonlinear transformation, so this is called the deeper methods, okay? And also we need to notice that all the method, all these complex encoders basically can be combined with the similarity function we discussed previously. So the focus for this part is not about the similarity functions. So we are focused on how we design the encoding functions. So all the similarity functions, basically we can use what we have discussed previously, right? So for example, we can use the random walk similarity. Okay. So before talking about the GM models, let's first quickly talk about some basics of the deep learning for the graph models, right? So if we want to develop some deep learning models, right, X is a data sample, right? So for example, it can be a vector. In the traditional machine learning, right, it can be a vector. And the theta is the parameter we're trying to optimize, right? And then through the parameter theta, we can try to find the relationship between the data sample X and the prediction target Y, right? So Y can be a classification target, it can also be a regression target. And we also have L as a loss function, right? So for example, we can make use of the cross entropy loss, right, for the classification problem, right? So then we try to minimize this function, right? So f here can be a simple linear function, right, like the MLP, and it can also be some advanced, more complex structure like the neural networks, right? So if we try to optimize this function, right, so typically we sample a mini batch of the input data sample X. And we first perform the forward propagation to compute the loss function given the data samples. And then we perform the back propagation, right? We obtain the gradient using the chain rule. And then we use some optimization tools like the stochastic gradient descent to optimize the function for the weights W, right? Over many iterations until that the loss function converge, right? So let's say if we have a graph, right? So we mentioned previously that the input is adjacency matrix, right? So let's, for the simplicity, we consider it's a binary. And addition to that, we also have another matrix X. So this matrix basically is a matrix for the node features, right? So we have a feature, some prior feature information for each node, right? So for example, if we have a social network, we may have some additional information about the users, right? It can be some profile information like the education background, the gender, uh, um, education background, the gender, demographic information of the users, right? It may also be some content information that the user post, right? And in a biological network, it can be some additional expression of the gene profiles, right? It can also be some functional information. And even in some cases that if we don't have any prior information of the node features, right? So we can also basically design some indicator vectors. Basically, it's a one-hot encoding of the node. Or we can use some constant vectors for all the nodes as input. Okay. So then if we have this kind of the graph, right, we have the adjacency matrix A and the feature matrix X, right? So if we want to design some deeper encoders, right? So one simple strategy here is that we can probably concatenate the adjacency matrix and the feature matrix together into a combined matrix, right? And then we probably can fit it into some deep neural networks, right? Like the MLP models, right? Although this kind of method is pretty simple, but it has some problems, right? So the first problem here is that the number of parameters is still linear to the number of nodes, and it cannot easily adapt to the graphs of different size because you can see that the size of this matrix based on different graphs, it could be different, right? And this kind of method is also sensitive to the node ordering, right? So if we switch the orders for the nodes, it may lead to totally different results. So if we look at the convolution networks on the image data, right? So the basic idea is that we can have some spectral filters, right? So let's say if we want to process this specific pixel, right? So we can leverage this spectral filter to look at all the pixels in this specific grid, right? And basically, this is a filter will basically perform some weighted summation of the pixel information in these grids, right? In order to get the information for the center node. So then the basic idea for the graph neural networks is that we're trying to generalize the idea of the convolution networks on the image data, right? Beyond this kind of the fixed and the simple lattice structure, okay? But we can look at this kind of the example, right? So if we try to design some filters on the graph, so I think one major limitation here is that if we design this kind of filter, for the graph data, there is no fixed notion of the locality, right? So basically, you cannot decide whether this node is basically uh, above this particular node or in the left position of this node, unlike the grids in the images, right? So there's no locality information, okay? And also additionally that another important consideration is that the graph is considered to be permutation invariant. So what do we mean by this? So let's talk about the permutation invariance first. So let's consider that if we want to get an embedding for entire graph, okay? So the observation here is that a graph does not necessarily have a canonical ordering of the nodes, right? So here's the example. Let's say we give a specific ordering for the graph, like the A, B, C, D, E, F, right? And this is another ordering. We give this node to be the label of A, B, C, D, E, F. So these are two different orderings of the same graph, right? So a desired characteristic for the graph is that if we want to learn some representations for the whole graph, right? So the learned representations basically for these two graphs, they are essentially the same graph, right? So the function should give the same embedding, regardless of how nodes in these two graphs are numbered, right? We should ignore the uh, node ordering, right? So then it comes with a definition of the permutation invariance. So let's say we have a graph, we have a function f, it takes the graph as input. So this is a adjacency matrix and this is a feature matrix. So we try to map the whole graph into a vector, right? So this is a function for the graph embedding, right? So this function is considered to be permutation invariant, right? If the function for the a and x and the function for the p transpose px, per p here is a permutation matrix p. Per p is a permutation matrix. So basically it gives different orders of the nodes, right? So basically p transpose will give us the adjacency matrix after the permutation, and px basically will give us the node features after the permutation, right? So we can see that we should keep the same embeddings after the permutation, right? So this is called the permutation invariance. So if the function basically can satisfy this, we can say that this function is permutation invariant. And there's another important consideration in the graph is called the permutation equivariance. So let's say we want to embed the nodes in the graph, right? So the desired property here is that the learned node representations basically should be the same regardless how the nodes are numbered. So still for these two different orders for the nodes, right? For this, let's say for these two green nodes, C and D. So this is numbered as C, but this is numbered as D in the second graph, right? So basically that if we have a function that tries to learn the node embeddings, so this function should give us the same embedding regardless how these two nodes are numbered, right? Although that they are numbered differently on these two graphs, but their embeddings should be the same, right? So then it comes with the definition of the permutation equivariance. So right now we can see that the function f will output the embedding for each node. So this function is considered to be permutation equivariant. If that the p multiplies the output fx equals to the f over the permuted adjacency matrix and the node attribute matrix. Right? So this is an illustration. Right? Let's say the relationship between these two different orders can be expressed through this kind of the permutation matrix P. So we can see that for the first graph, right, A1, X1, so if we get these embeddings, and for the second graph, F A2, X2, we get these embeddings, right? So basically that the same node, C and D, so they should also be connected through this permutation matrix P. Okay, so this is called the permutation equivariance. So if we design an embedding function over the graph, so they basically should satisfy the permutation equivariance and the permutation invariance. Right? So this is a summary about these two desired properties. For the graph level functions, we should satisfy the permutation invariance. And for the node level function, we should satisfy the permutation equivariance. right? So here are some examples. For example, for the function 1 transpose x, so this is a permutation invariant function. You can verify. And this is fx equals to x. If we just use the node features, so this is a permutation equivariant function. Okay, and ax basically is also a permutation equivariant function. So okay, so if we design some graph neural network models, basically it will consist of multiple permutation equivariant and invariant functions. Right? If the function is basically trying to learn the node embeddings, it should be permutation equivariant. And if we try to aggregate the embeddings for the whole nodes into a single embedding, right? So it should satisfy the permutation invariance. Okay, so before we look at some detailed design for these functions, so we can check are other neural network architectures like the MLP models, are they permutation invariant or the permutation equivariant? So here is an example, right? So let's say we have the same input, right? Same feature input. So you can see that the inputs are the same to these MLP models, right? So the numbers are the same. We have three features, but here that we're trying to switch the orders for the inputs, right? So we have three different input orders. So you can see that through the MLP model, right? So all these three different the same. This is the same MLP model. So the switched input basically we need two totally different outputs, right? So in the other words, that the MLP models are not permutation invariant or equivariant. Okay, so that explains that why this kind of the simple MLP approach does not work for the graph data, right? So even that the method can handle the graphs of different size, but if we basically switch the orders for different nodes, it will lead to totally different results if we just relied on the multi-layer perceptron. Okay, so to solve this kind of problem, it comes with the seminal work called the graph convolution networks. So it's published in the iClear conference. It's a top machine learning conference in 2017. So the basic idea for this approach is that we're trying to define um, a computation graph for each node. So essentially that the computational graph is just the one hop, k-hop neighbors for each node, right? So here, let's say for the node I, so this circle denotes the one hop neighbors, right? And this node basically denotes the second hop neighbors, right? So these nodes with colors are denote the nodes that have the class labels. So these the nodes with no color denotes the unlabeled nodes. Okay, so the first step is that we're trying to define the computational graph, right? And then after we have the computation graph, then we perform the message propagation and the transformation within this computation graph, right? So let's say if we're trying to learn the embedding for the node I, we're trying to propagate the information of other nodes in this computational graph. And then we're trying to perform some transformation. So in a way that we can aggregate the information for all the nodes in the computational graph together. Okay. So more specifically, that this kind of methods will help us to learn how to propagate the information across a graph to compute the node features. Okay. So this is the key idea for this kind of the method, right? So it's called the neighborhood aggregation, right? So let's say if we want to learn the embedding for the node A, so what we can do here is that we can first define the computation graph, right? So we can see that for the node A, if we look at the first order neighbors, that is B, C, D, right? B, C, D. And for the node B, we also look at its first order neighbors, which is A, C. And for the C, the first order neighbors will be A, B, E, F. And for the node D, the first order neighbor will be node A. So basically, if we only consider the neighborhood size as 2, this is the computational graph for the node A, right? And then if we trying to learn the embedding for the node A, so we trying to first find a way to aggregate the information from its first neighbors, first order neighbors, which is BCD, right? We're trying to fit this information together, trying to find a way to aggregate them. And then we get the embedding for the node A. And also recursively, if we're trying to find the information for the node B, right? So we also trying to look at the first order neighbors for the node B, right? So we're trying to aggregate their information together, trying to get the information for the node B, right? So we can see that the gray box here are all the aggregation functions. Okay, this kind of aggregation functions can be designed using some neural network models. Okay. So as we mentioned that the basic idea is trying to define a computational graph for each node, right? So for each node, basically we have a computational graph, and we're trying to design some modules to do the neighborhood aggregation and the transformation within this computational graph. Okay? And also for this kind of models that the model can be arbitrary depths, right? So for this example, it's just a two-layer model, right? Because we only consider the two hop neighbors, right? So basically, we can see that the nodes has embeddings at different layers, at each layer, right? We have the embedding for the node A at this layer, we have the embedding B, C, D at this layer, and also embedding at this layer, right? At a layer zero, right? So the layer zero basically of the embedding, basically we use its input features, right? Remember that previously we talked about some, let's say, user profile information, right? So if we know this kind of information, we can consider them to be the layer zero embeddings, right? We take these embeddings as input, okay? And the layer k embedding basically will get the information from the nodes that are k hops away, okay? And then we can take a look at this kind of the neighborhood aggregation mechanism, right? So different methods actually, their difference is that how they aggregated the information across layers, right? More specifically, that different methods differ how we design the function within this box, how these functions are designed. Okay, so one basic approach that we can design is that we can average the neighboring information uh, and then apply a neural network model, right? So basically, let's say if we want to get the embedding for the node A, we can try to get the embedding for the B, C, D in the previous layer, right? We take the average, and after that, we, let's say, apply some neural network modules, perform some nonlinear transformations. So it comes with this basic approach, right? So this is the superscript denotes the layer zero, right? So we can see the layer zero for the node V is initialized with the input feature, right? And then this is the updated rule for between the layer K and the layer K minus one, right? So we can see that if we want to learn the embedding for the node V in the layer K, so for the first part, we're trying to do the average of the embeddings of its neighbors in the previous layer, right? So this is the average. And then we multiply it with the transformation matrix WK. So this is WK is for the neighbors. And also we're trying to leverage the information of the same node in the previous layer, right? And multiply with another transformation matrix BK. And then we trying to fit the summation into a nonlinear transformation function. Right? It can be a ReLU function, sigmoid function, or the 10H function. Okay. So then we can look at what are the invariance and the equivariance properties for a GCM model. Right? So this method is called the graph convolution network. So given a specific node that we can see that the GCM model will compute its embeddings. The GCM model computes its embeddings is permutation invariant, right? So here we can see that this kind of the aggregation function is typically considered to be the permutation invariant. And then this kind of the transformation function is considered to be permutation equivariant. Okay. So then another question we're trying to answer is that how can we train this kind of model? Right? How can we train the model to generate a high quality embeddings? So if we already know the propagation rule for the GCM model, how can we train these embeddings? Right? So this is basically the updated rule, right? So we have the embedding for the layer zero, and we also basically can apply this function recursively across k different layers, and until at the end we have the embeddings for all the nodes, right? So after k layers of neighborhood aggregation, so we can get the output embeddings for each node. And we can feed these embeddings into any loss function and run stochastic gradient descent to train aggregation parameters. So essentially, the WK and the BK are the parameters we're trying to train, right? So this is a kind of the matrix formulation of the previous updated rule, right? So if we trying to put the embeddings for all the nodes in the layer K into a matrix HK, right? So we can see that the updated rule between two different layers can be represented as this. So D is a diagonal matrix. So each entry is node degree. A is a adjacency matrix. Okay. So then we can have update the function in a matrix form, right? So A tilde basically is a normalized adjacency matrix, okay? And WK minus one and BK minus one basically are the parameters we're trying to learn. And in practice, that this formulation also implies that this kind of the matrix operation, right, is based on some sparse matrix because A tilde, because the graph adjacency matrix is typically very sparse, and A tilde is also very sparse. So it's based on some sparse matrix multiplications, right? But we should be careful that not all the GM models can be expressed in a single matrix form, right? Unless that the aggregation function are in a specific desired form, and we can write down the matrix formulation, right? Okay, so then back to our problem, how do we train the GM model, right? So let's say we get the updated rule to get the embedding for each node, right? So ZU basically is a function of the input graph, right? So we can perform the unsupervised training, right? So if we don't have any class labels, if we don't have any labels for the nodes, so we in this case we can use the graph structure as the supervision signal, right? And on the other hand, if we have the supervised signals, let's say already know a subset of nodes has a class label, we can basically formulate a supervised loss function. Y is the node class labels, right? L can be L2 norm function if Y is a real number, or if it's a classification target, we basically can use the cross entropy loss. So the basic idea is that the similar nodes, they should have similar embeddings, right? So let's say if we don't have any, let's say if we don't have any class labels, right? So YUV denotes that the two nodes, how they are similar with each other in the original graph. So we're trying to ensure that the this, the node embeddings after the decoder function, for example, the dot product, can well approximate the similarity of the nodes in the original graph. Right? So this is essentially what we have discussed previously. Right? And for example, the C is it can be the cross entropy loss. Okay? Y is the actual ground truth, and the F theta xi is the predicted values. Okay. So this is another case, right? How can we train this model in a supervised manner, right? So let's say we already have some class labels for the nodes. So for example, if we want to train a bot detection model to decide whether a node is a bot or human, right? We already know some labels of the nodes. For example, we already know B, C, D, E, F, they are class labels, right? So we can formulate a supervised loss function, and then we can try to help us to decide whether the node A belongs to human or bot, right? So more specifically, let's say if it's a binary classification problem, we can actually make use of the cross entropy loss, right? So YV, basically when YV equals to 1, so we're trying to maximize this kind of the um, dot product, right? And if Y equals to 0, we're trying to minimize it, okay? So this is the overview of the model design for the GM model, right? So we can see that in the first step, we're trying to define a neighborhood aggregation function. And then we're trying to design a loss function based on the node embeddings, right? And after that, we can train the model based on a set of the nodes, right? If we already know some specific class labels for the nodes, we can formulate the loss function, right? And after we train the model parameters, so we can see that this model can help us to generalize to learn the embeddings for other unlabeled nodes, right? So even for the nodes that we have not seen previously. Okay. So in the other words, that this kind of models, right? So they do not learn embedding vector for each node. So instead, they trying to learn some shared aggregation parameters between for all the nodes between different layers, right? So let's say we take this example, this architecture as example, right? So let's say between this layer and this layer, we're trying to learn the shared parameters, the transformation parameters, WK and BK. So these two metrics, their size is actually independent of the node size. So their size is only dependent on the node embedding dimensions between these two different layers. So in the other words, that the number of model parameters we're trying to learn right now is sublinear in the number of nodes. And also because that the number of parameters we're trying to learn is independent of the node size. So after we learn these node embeddings, we can apply the updated rule, right, from the first layer to the last layer. And then we can generate the embeddings for the unseen nodes. So in the other words, that this kind of the model actually has the so-called inductive learning capability, right? So they can actually help us to learn the embeddings for the new nodes that do not even appear in the graph previously, right? And it also means that we can basically to generate the embeddings for the new nodes on the fly, right? So if let's say if it is a social network, there are many new users join the network, right? So after we train the model, right? Let's say on this snapshot, so if some new nodes arrive, basically that based on the connection of this new node to the existing nodes, we still can generate the embedding for this new node. Okay, so as a summary, that for the GCM model, right? So we're trying to design some unit hook modules by defining the aggregation function. So the aggregation function between two different layers is designed in this way. Okay, so this function, after this updated rule, we can formulate some loss function, right? So if it is an unsupervised task, basically we can make use of the supervision signal on the graphs, right? Basically that is the node similarities. And if we have some class labels for the nodes, we can formulate a supervised loss function, right? And then we can train a neural network to optimize the model parameters, right? And after we train the model parameters, so we can generate the embeddings for the new nodes. So then the question here is that can we design some other aggregation functions? So this is a very simple aggregation function, right? So this is we do the average of the embeddings for the neighbors, and we multiply WK and the embeddings for the same node in the previous layer multiplied with BK. Can we design any other aggregation functions? So before that, let's take a quick break. Let's probably take a 10 minutes break, and then we'll come back. And also, if you have any questions, you can probably type your questions in the chat box, and I will answer it later. Yeah, I think we can come back at 9 55. Okay. Okay. Uh, yeah, I think let's continue the discussion. So right now, I think we'll move to the third part. So I will basically discuss a general design principle of the GM model, right? So after this part, you will basically have, I should be familiar with different general design principles of different GM models. So in this way that you probably can also come up with GM model that best fits your application. Okay. So this is a general design pipeline for the GM model. Right? So here we can see that there are five essential components. So the first part is about the message passing, right? And the second part is about the aggregation. And then we also talk about how can we stack different layers together. And then we also talk about how can we perform the graph augmentation. And after that, we'll talk about the learning objective. So we can see that for the first two parts, it's basically within a specific GN layer, right? So basically that we have a message passing layer, and we also have the aggregation function, right? So there are different instantiations under this perspective, right? So we'll talk about the GCN graph stage and the GAT model. So the basic idea of the specific GN layer is that we're trying to compress a set of vectors into a single vector, right? So there are two steps in this specific process. So the first process, we call it the message process, right? And the second part, we call it the aggregation. So for the message part, right? So we're trying to uh, so message basically is the embedding for the nodes itself in the previous layer, or the embeddings for its neighbors in the previous layer, right? And then we can see that we put all this message into this bracket, and then we trying to find a way to aggregate this information together. Okay. For the message computation, we can see that and the basic message function here is that let's say we have the embedding for the node U in the layer L minus one, right? So here that each node will get a create a message, right? It will be sent to other nodes later, right? So one simple example is that we can perform a linear transformation for the message, right? For example, using the matrix WL, right? So all the loads will basically multiplied with the same weight matrix. And for the aggregation function that the node V will basically aggregate the message from its neighbors, right? So for example, we can do the summation of all the message, right? And we can also take the min or the max aggregator, right? So there are different options here. So the issue here is that for this kind of the message and aggregation process is that the information from the node V itself could get lost, right? Because the computation of the HVL does not directly depend on the embedding of the same node in the previous layer. So the solution here is that we probably need to include the embedding for the same node in the previous layer when we create the embedding in the next layer. Right? So more specifically that we can see that we can also need to compute the message from the node V itself. So usually that we have a different computation function for the neighbors and for the same node itself, right? So for example, for the neighbors, we can use the WL, and for the same node in the previous layer, we use the BL. So these are the two transformation metrics we discussed previously, right? And for the aggregation function, right? So after aggregating from the neighbors, we can also aggregate the message from the node itself, right? Either using a concatenation function or using a summation function, right? So here in this example, we first do the aggregation for the message from its neighbors, right? And after that, we also concatenate with the message of the same node in the previous layer, right? Through the concatenation function. So putting all this together, right? So in a single GN layer, so basically we have these two essential components, the message function and the aggregation function, right? So typically these functions are also combined with some nonlinear transformation function to increase the expressiveness of these representations, right? So typically that this function are using basically we can use some nonlinear transformation functions like the ReLU function, sigmoid function, so they have the same notation here, and they can be added to the message or the aggregation. So here are some most widely used nonlinear activation functions, right? So this is the ReLU function. Basically, the value is 0, right, when it is smaller than 0. And the value is equals to x when it is larger than 0. And we can also use a sigmoid function, right? Basically, we can restrict the value within the range of 0 to 1. And we can also use a more advanced parametric ReLU function. Right? Basically, we have a specific parameter to control the slope of the function when it is smaller than 0. Okay. And then we can take a look at some classical GNN models. So the first one is the GCN model, right? For the GCN model, the aggregation function is written as this, right? So the question here is that how can we write this as a message plus aggregation design principle? So we can see that we can consider this part, right? So the average of the embeddings in the labels of the previous layers multiply the WL as a message function, right? After that, we basically do the summation. The summation basically is aggregation function, right? So this is some details of this kind of the how can we fit the GCM model into this design principle. Okay. It should be noted that for the GCM model, that the input graph is assumed to have the self edges, right? So typically that because the graph is assumed to have the self edges, so typically we do not include the embeddings of the same node in the previous layer into the summation function. Okay. And we also have an advanced approach. It's called the graph sage, right? It's basically a follow-up work for the GCM model. So this is the updated rule for the graph sage function. And we can also try to fit this function into this kind of the two-stage procedure, right? For the first part, we aggregate from the node neighbors, right? So let's say if U is a neighbor of the node V, we're trying to find a way to aggregate the embeddings for the node in the previous layer. And um, and also we can try to concatenate with the node representations of the same node in the previous layer. We can concatenate them together, multiplied with another transformation function WL, right? So then the question here is that how can we fit into the message and aggregation principle, right? So here that for the aggregation function, typically we have different kinds of design principles, right? For the aggregation function, the most simple way is that we can do the weighted average of the neighbors, right? So each node basically uh, is normalized by the degree for its neighbors, the degree of the center node, right? And we can also design some more complex aggregation function, right? So for example, we can transform the neighbor vectors and apply some symmetric vector functions like the min or max, right? We can first perform the MLP over the node embeddings, and then we can fit it into another aggregation function. And in order to improve the expressiveness of the aggregation function, so this paper also introduced another method. It's called the LSTM. But it should be noted that LSTM basically is not a symmetric function, right? So basically, typically we need to reshuffle the node neighbors, right? So here, basically that we're trying to look at its neighbors and reshuffle it, and then fit it into LSTM function. So basically that we consider that the neighbors as a sequence. And for the graph stage model, they also have the L2 normalization design. So at each layer, they try to normalize the embeddings. So ensure that all the vectors have the same L2 norm. So in some cases that they found that the normalization can result in performance improvement. And now we want to talk about a more advanced approach. It's called the graph attention network. So this is the updated rule for the graph attention network. It's also called the GAT. So here that the alpha VU is called the attention weights. Okay. So we can notice that in the GCN or the graph stage, so this parameter alpha VU is typically a fixed number, right? So for example, in the graph stage, GCN, so this number basically is 1 over the size of the neighborhood of the node V. This is a weighting factor, denotes the node use message to the node V, right? So so in the other words, that in the GCN or the graph stage, this parameter is defined explicitly based on the structural properties of the graph, especially the node degree, right? So all the neighbors of the node V basically are equally important to the node V, right? But for this method, right? So the basic idea here is that they consider that different node neighbors are not equally important, right? So it is designed by the cognitive attention in the psychology, right? So this is also called the attention mechanism. It's also widely used in the modern transformer design. Okay, so basically that this attention weight alpha VU focus on the important parts of the input data, and it tries to fade out the remaining part, right? So it selectively learns the most important part uh, in aggregation. Okay, so the basic idea is that the neural network should devote more computation power on the small but important part of the data, while putting some less efforts on the remaining part. Okay, so which part is more important? Basically, this parameter is basically totally depends on the context, and the parameter is also learned during the training process. Okay, so then the GAT basically tries to address the key question: Can we learn some better simple aggregation functions, right? Can we let the weighting factors alpha VU to be learned implicitly? So the goal here is to specify arbitrary importance to different neighbors of each node in the graph. So it tries to compute the embedding for each node in the graph following the attention strategy. Okay. So more specifically, nodes will attend over their neighborhood message, and it will help us to implicitly specify in different ways different nodes in a neighborhood. So then the question here is that how can we learn the attention weight alpha VU, right? So this weight basically is can be computed as a byproduct of attention mechanism A. A is basically a function, okay? So A actually computes attention weights EVU across pairs of the U and V based on their message, right? So basically we can see that for the U and V, we'll take their embeddings in the previous layer, multiplied with a transformation matrix WL, and then fit it into this function A, right? And then we can learn this kind of the attention coefficients. So this attention coefficients indicates the importance of the node use message to node V, right? So for example, for the node A, right, when we're trying to aggregate the information from its neighbors, so it has the three neighbors, um, uh, B, C, D, right? So we can see that we can specify different attention coefficients to different neighbors. Okay, so basically it can be learned through this attention function. And also that because the attention weight typically is should be considered as a number that is between 0 and 1, right? So we should ensure that for all the neighbors, the summation of the attention weights should equal to 1, right? So in other words, we need to normalize this attention weights. So how can we do this? So basically, we can use the softmax function, right, to feed the attention coefficients into this softmax function, right? So then we can get a normalized attention weights, right? And after we get the attention weights, then when we do the message aggregation, we can basically use this rule, right? So for example, then we can see that when we learn the embedding for the node A, right? So we can learn the alpha AB, alpha AC, and alpha AD, right? It will specify different importance to these three different neighbors, right? And then basically we can selectively focus more on the neighbors that has higher attention weights. It will contribute more when we learn the embedding for the center node A. Okay. So then the question here is that how should we design the attention mechanism or the function A, right? So I think there are some simple strategies. So the simple strategy here is that we can use a single layered neural network, right? So A basically also has some trainable parameters, right? So this is a simple design of the attention mechanism A. So what we can do here is that if we want to learn the attention coefficients EAB, right? So we first take the transform the embeddings for the nodes from the previous layer. We try to concatenate them together, and then we fit it into a linear function, right? So in the other words, that the attention mechanism only has a trainable parameter that is the, respect to the linear layers, okay? And the parameters of the attention mechanisms can also be trained jointly with the weight matrix, right? With the weight matrix of the GM model in an end-to-end manner, okay? And also, in many situations that typically people also introduce the so-called multi-head attention mechanisms. So basically, instead of just learning one single attention weight, so they will learn multiple attention weights because that they found that by learning multiple attention weights, it will basically make the training process to be more stable, right? So after we learn the multiple attention weights, we basically learn the embeddings for each attention head, right? So then in practice, we try to aggregate all these attention, aggregate all these embeddings correspond to different attention heads together, right? So for example, we can use a concatenation or the summation. So let's have a summary about the benefits of the attention mechanisms. So the key benefit here is that it will allow us to implicitly specify how different neighbors will contribute to the center node's information aggregation process. So, and also this process is computationally efficient, right? So the computation of the attention coefficients basically can be parallelized across all the edges in the graph, right? And aggregation may also be parallelized across all the nodes. And the storage is also efficient. So here that we only need to perform the sparse matrix operation, and it does do not require more than O V plus E entries to be stored, right? So the storage-wise is also efficient. And also similar to the GCM model or the graph sage model, it actually has a fixed number of parameters. So the number of parameters is also uh, irrespective of the graph size. And also that this kind of method also provide a localized way to aggregate the information from the neighbors, right? Because that we only trying to attend over the local neighborhood by selecting the most important neighbors, right? If we want to capture the long-term dependencies between the nodes, we can actually stack multiple GAT layers. And similar as other models, it also has the inductive learning capability, right? So it can also help us to generate the embeddings that for the nodes that do not appear in the training data. Okay. Okay. So next, I want to talk about how can we design the GN layers in practice. Okay. So in practice, that these classical GN layers are great starting point, right? So we can actually get a better performance by considering a general GN design. Okay. More concretely, we can include some modern deep learning modules that has shown to be useful in many domains. So this is an illustration about a suggested GN layer, right? So we can see that it has many different operations we can apply. So in modern deep learning modules, right? So many functions or many tricks can be applied. So for example, we can use a batch normalization. So basically it will stabilize the training, and we can also use a dropout. It will prevent overfitting, right? And similar to GAT, we can include the attention or even the gating mechanisms, right, to control the importance of different messages. Okay. So let's first talk about the batch normalization, right? So the batch normalization basically is used to stabilize the neural network training, right? So the key idea is that after we, for each batch of inputs, right? So we can recenter the node embeddings into zero mean, right? We can compute the mean, and then we rescale the variance into unit variance, okay? So the first step is that we compute the mean and the variance over n different embeddings. N is the batch size, right? And after that, we can normalize the feature using computed mean and variance, right? So basically, in the other words, we do the normalization for each data batch. So people found that this kind of trick can stabilize the training. And the second trick we can apply is called the dropout. Dropout is also a very used technique to prevent the overfitting of the neural network training, right? So the key idea is that during the training, right? So let's say each node denotes some neurons of the MLP model, right? So during the training, for each neuron, it has some probability p to be randomly uh, turned off. Turned off basically means that the neurons, the value will be directly specified as zero. So we will cut the value and its connections to other neurons. And during the test, we will use all the neurons for the computation. Okay. And we can basically plug in the dropout technique for the GN training, right? So in the GN, dropout is typically applied to the linear layer in the message function, right? So especially when we multiply the neighbor embedding to the transformation function WL, we can apply this kind of the dropout trick. Okay. So as a summary that many modern deep learning modules can be included in a GN layer in order to achieve better performance, right? So designing a novel GN layer is still very active research frontier. So so you can explore different GN designs and trying to figure out which one basically achieves the best performance. Okay. And after that, I will also talk about the third component of the whole design. It's about how can we stack different GN layers together, right? So I think one simple idea is that we can just stack layers sequentially, right? We can stack multiple layers. And another strategy is that we can add in some skip connections. I will talk about more about it later. Okay. So how can we construct a GN? As we mentioned, as the traditional way is that we can stack different GN layers one by one, right? So the initial embeddings are the node features, and this is the first layer GN, second layer GN, third layer GN, right? So we can, after multiple layers, we can improve the expressiveness of the embeddings. But this kind of design principle actually has an issue. It's called the over-smoothing issue, right? So the over-smoothing issue happens when we stack multiple GN layers. So the over-smoothing issue says that all the node embeddings, right, especially when we stack multiple GN layers, when the GN layers becomes very deep, all the node embeddings will converge to the same value. So this is actually undesired, right? Because if all the values are the same, basically it means that we cannot differentiate the nodes anymore, right? So basically that if we apply the embedding to any downstream task, the performance will be greatly affected. So then the question here is that why we have this kind of over smoothing issue? So the over-smoothing issue is actually related to the receptive fields of the GM module, right? So the receptive field actually is a principle actually originated from the convolution network. So in the context of the GN, receptive field denotes a set of nodes that determine the embedding of a node of interest, right? So let's say we have just a one layer GN. So the receptive field for each node will be its one hop layers. But if we have a k-layer GN, so each node basically has the receptive fields of its k-hop neighborhood, right? So we can imagine that if k becomes very large, right? So then the receptive fields for all the nodes basically will become the same, right? So let's say if we have 10, 20, right? Because the shortest path between any two nodes in the graph typically is considered to be a very small number. If that k, the number of k becomes very large, the receptive fields for all the nodes are the same. So then it means that when we do the message aggregation, so the embeddings for all the nodes in the limit, it will converge to the same value. Okay. So this is called the over smoothing issue. So so then the question here is that how can we mitigate this kind of over smoothing issue, right? So the solution here is that the first solution here is that we can try to increase the expressive power within each GN layer, right? So in a way that we don't need to stack many different layers. Probably we can just stack 2 or 3 layers. That is good enough. So here that we can turn the aggregation transformation functions into some deep neural networks. We're trying to make each layer to be more powerful, right? And the second strategy here is that we can add some layers that do not pass message, right? We can probably do some pre-processing, and we can also do some post-processing, right? So these layers basically will not propagate a message. We still just use a few GN layers, but we actually do some additional operation for the pre-processing and post-processing. And the third strategy here is that we can add some skip connections, right? Skip connections basically is inspired by the residual, uh, by inspired by the convolution net, the advance in convolution neural networks. So the observation here is that they found that from the oversmoothing is that the node embeddings in the earlier GN layers can sometimes better differentiate the GN modules, right? So they found that some earlier layers are more useful. So therefore that they trying to add some shortcuts from the earlier layers to the later layers, right? So this is example, right? So this is the first GN layer. So we're trying to add some highway skip connections from the first layer to the second layer, right? So this is an illustration, right? So you can see that for the final output, right, it's a summation of two different branches, right? We not only have the function after different operations, and we also add a highway from the input plus x, right? So in other words, that there is another connection from the first layer to the last layer, right? So this kind of idea is called the skip connection. So with skip connection, it allows us to basically stack a very deep learning and very deep GM modules. So why the skip connection work? So basically that the skip connection basically can be considered as an idea that will create a mixture of modules, right? So let's say we have n different skip connections. So basically that there are 2 to the power of n different possible passes between the input to the output, right? Because each skip connection can be turned on or turned off, right? And each pass could have up to n different modules. So in other words, that we automatically get a mixture of the shallow GM module and the deep GM module, right? So this is an illustration. And there are some other options for the skip connections, right? For example, we can directly skip to the last layers, right? For all the intermediate layers, we can directly skip to the last layers. So it sometimes it may also improve the expressive power. Okay, we still have around 40 minutes, so then we'll talk about the last part about the GN augmentation and training. So this is the general GN framework, right? We can see that after we get the embeddings, right, we need to design a loss function, right, in order to minimize the loss function to train the parameters of the GN module, right? So far we have discussed how to learn the embeddings, right? And right now we want to focus on how can we perform the prediction tasks. So as we mentioned previously that we can perform different levels of task on the graph, right? We can perform the node level task, edge level task, or the graph level task, right? So different tasks require different prediction heads. So let's first look at the node level task, right? So let's consider that we have a k-way prediction task, right? So for example, we want to classify the nodes into k different predefined classes. Or let's say we have a regression problem. We have k different regression targets, right? So if we have a k-way prediction problem, so we can design a prediction head, right? So let's say after the GNN model, right, we can get the embedding for all the nodes in a d-dimensional space for each node, right? So then the question here is that how can we map the embeddings to a prediction target, right? So for the node level task, right? So here we can multiply the node embeddings into a transformation matrix, right? So this is WH. We call it the transformation um, matrix for the prediction height, right? it will map the node embeddings in the prediction results. And after we have the predictions, we can calculate the loss function, right? And also for the age level task, right? Let's say we can also do the K-way prediction, right? But here that the input, because this is an age level task, for the input, we need to take the embedding for the two end nodes, right? The source node and the end node, U and V. So the prediction head basically should map the embedding for these two nodes into a prediction target, right? So the first option is that we can probably concatenate these two vectors and then perform some linear transformation, right? We can get the prediction. And we can also directly take the inner product of the two vectors. But for this option, it only applied to the one-way prediction, right? For example, we just predict the existence of the age, right? And if we want to perform the K-way prediction, basically that we need to perform this kind of operation, right? So we multiply the HU, the transpose of the first vector, and put the transformation matrix in the middle, right? So this matrix is trainable for the ice prediction entry. Basically, we have a transformation matrix for each entry. Okay. For each prediction target. And for the graph level task, right? So let's say we also have a K-way prediction problem, right? So now we want to find a way to aggregate the embeddings for all the nodes together, right? So previously we talked about some simple strategies when we talk about the node embeddings, right? But here we want to provide some general principles here. So there are many different design principles, right? For example, we can do the mean aggregation, right? We can take the average for the embeddings, and we can do the max pooling, right? We can, for each dimension, we take the maximum value, and we can also do the sum pooling, right? To do the summation of all the embeddings, okay? But there are some issues for this kind of, so this kind of approach is called the global pooling, right? Because they actually just do the pooling in one time, right? So this is called the global pooling. So the global pooling, the issue of the global pooling is that it may lose some important information. So let's look at this example. So let's say we have the embeddings for two graphs, right? This is just a one-dimensional embedding. So we have five nodes, -1, -2, 0, 1, 2, right? So five nodes. And for the second graph, we also have the values for five different nodes, right? So we can see that these two graphs have different node embeddings, right? Um, so in the other words, that their structure should be quite different, right? But let's see that what will happen if we do the global summation pooling, right? For the first graph, if we do the summation pooling, the value will become 0, right? And for the second graph, we will also have value of 0. It means that these two graphs with different embeddings, after the global pooling, their values will become the same. It means that they become indistinguishable, right? So what should we do? So the solution here is that we can design the so-called hierarchical pooling strategy. So in the other words, that we're trying to aggregate the node embeddings in a hierarchical manner, right? So for example, that we can divide the graph into two different parts, right? So we can consider the first node in the first part and the last three nodes in the second part, right? So let's say we do the aggregation with the summation and after multiply the ReLU function, right? Let's look at the first graph. For the first two entries, right, we first do this kind of the global pooling, we get a value of 0. And for the last three entries, after this operation, we get a value of 3, right? And then for these intermediate results, we will do the pooling operation again. We'll get a value of 3, right? And then for the second graph, right, we can also do um, the pooling for the first two entries and then the pooling for the last three entries. And then for these two intermediate results, we do the pooling again. So now we have a value of 30. So you can see that with this kind of the hierarchical manner, we actually have the pooling results that are different, right? For these two different graphs with different structures. So in the other words, these two graphs right now becomes distinguishable. Okay, so this is the basic idea of the differential pooling. So it tries to find a way to hierarchical pool the node embeddings. So more specifically for this method that they maintain two different GN modules. So for the GNA, so for the first GN module, it is responsible to compute the node embeddings. While for the second module, right, it tries to compute the clustering structure that a node belongs to. So unlike the previous two example, we just specified the node clusters. But here that for this method, it will automatically learn what is a suitable cluster structure through the second GM module. Okay. Okay. So then they train these two GM modules together, right? So in this way that they can get the uh, final representation for the whole graph and for the graph classification problem. Okay. And then if we look at the prediction problem, another important part is that we actually need to find some supervision signal in order to formulate the loss function, right? For the training labels, for the supervised learning tasks, labels actually come from some external sources, right? So for example, if we want to predict the drag likeliness of a molecular graph, we actually have the prediction target for each molecular graph, right? But for the unsupervised learning problem, so the signals actually come from the graphs themselves, right? So for example, if we want to perform a link prediction problem, right? We want to predict whether two nodes are connected with each other. So the prediction target basically in the graph itself, right? We already know that whether some nodes are connected with each other in the graph or not, right? We just consider the existing edges as some supervision signal, okay? So sometimes that the difference between the supervised learning and the unsupervised learning are kind of the blurry. Okay, so we still have the supervision signal in the unsupervised learning, right? So for example, we want to train a GM module to predict the node clustering coefficient, right? We can compute the clustering coefficient from the graph itself, right? And then we fit the clustering coefficient as the prediction target, right? So sometimes that people also call this kind of the training paradigm to be the self-supervised training. Okay, self-supervised means that the supervision signal are from the data itself. So for the supervised labels that, as we mentioned, that it come from some specific use cases, right? For example, for the node label in a citation network, so the class label denote which subject area the paper belongs to. So for the age label, that for example, in a transaction network, it knows whether an age is fraudulent or not. And in a graph label, in a graph problem, that the graph label denote the drag likeliness of a graph. And the advice here is that you should reduce your task to node edge or graph labels. So since that they are more easily to work with, right? So for example, if we know some nodes from a cluster, then we can treat the cluster a node belongs to as a node label, right? And for the unsupervised signals, sometimes we only have the graph without any external labels, right? So as we mentioned, this is also called the self-supervised learning, right? So for example, for the node level task, right, we can consider some external node statistics like the clustering coefficient or the relative importance of the nodes as some supervision signal. For the edge level task, we can consider we can try to hide the edges between two nodes and then trying to predict if there should be a link between them, right? And for the graph statistics, right? For the graph level task, we can consider some graph statistics like if two graphs are isomorphism to each other, right? So these tasks do not require any external labels, so they can be basically designed from the data itself. Okay. So then the next question here is that if we know the labels, how can we formulate the loss function, right? So for the classification loss, basically we can make use of the cross entropy loss, right? So J denotes the ground truth and the Y hat denotes the prediction, right? So this is basically the prediction and the ground truth and the prediction. For the prediction, we use a softmax, right? So this is basically a probability distribution. So one way is that we can make use of the cross entropy loss to compute the difference between these two different distributions. And for the regression problem, right? So this is basically an example. We can make use of the mean squared error to compute the L2 norm difference between the prediction target and the ground truth. And after we formulated the loss function, right, we can train a model. And then the important part of the GN model is that how can we measure the success of the GN model, right? How well are the trained model parameters? So therefore that we need to basically use some external metrics to do the validation, right? For the regression problem, we can use the root mean square error or the mean absolute error, right? IMSE and MAE, these are two widely used metric. For the classification problem, we can use, for the binary classification, we can use the accuracy, precision, recall, F1 score, or the ROC, AOC curve. And for the multi-class class classification, we can use the accuracy or the micro and macro F1 score, right? Okay. At last, I want to briefly talk about how can we setting up the GM prediction task. So most specifically, we want to talk about how should we split the data set into the training, validation, and the test set, right? Because this is a little bit tricky compared with the training process of the image or the text data. So more specifically, we have two different kinds of the strategies. So the first strategy is called the fixed split. So we will just split our data set once, right, into the training set, validation set, and the test set. So the training set is used to optimize the GM model parameters. And the validation set is used to decide what are the best model hyperparameters, right? Uh, and then the test sets basically are held out until we report the final performance. So a concern here is that sometimes we cannot really guarantee that the test set will be really held out. Okay. And another strategy here is that we can also do the random split. We can randomly split our data set into the training, validation, test. And then we report the average performance over different random seeds. Okay. I would say that both strategies are widely used in many papers. So actually, I want to mention that the data split for the graph data is a little bit special, right? So before that, let's first think about that we want to split an image data set, right? So let's say we have an image classification problem. So each data point here denotes an image, right? Suppose we have 6 different images, right? So we can see that the different data samples or different images, they are independent with each other, right? So let's say the first two images are used for the training, and then three and the fourth, third and the fourth image are used for the validation, and we have the 5 and 6 for the test. So we can see that for the test set, right, image 5 will not affect our prediction on the image 1 because they are independent with each other. But this is not the case in the graph data, right? So let's say we have a node classification problem, right? So each data point is a node, right? So here that different nodes, they are not independent with each other, right? So let's say we still have this kind of data split, 1 and 2 into the training set, 3 and 4 into the validation set, and 5, 6 into the test set. So we can see that because there are some edges between these 3 different sets, when we do the test, node 5 will also affect our prediction on the node 1, right? Because when we do the message passing to learn the embedding for the node 1, it basically depends on the embedding for the node 5, right? So then what should we do? Because there are some dependencies between these different data splits. So actually, there are two different data split strategies. So the first solution is called the transactive setting. So basically, we assume that the input data graph can be observed in all the data splits, okay, including the training, validation, and test. And we only split the node labels. What does that mean? Take this graph as example. So at the training time, right? So we can compute the embedding using the entire graph and using node and 1, node 2's label. And during the validation time, we compute the embedding using the entire graph also. And we evaluate on the node 3 and node 4's label. And when we do the test, we still have the whole graph. And then we're trying to predict the node 5 and 6 label, right? This is the first setting, it's called the transactive. And for the inductive setting, what we do here is that we break edges into splits to get multiple graphs. So now we actually have 3 different graphs that are independent. So in the other words, that we ignore the connections between these different splits. So these edges, these gray edges, basically we ignore them, right? So during the training time, we compute the embedding just using the graph with the node 1 and node 2, right? And also their neighbors. And during the validation time, we basically compute the embeddings using the graph over the 3 and 4, and then we evaluate on these 2 nodes neighbors. And during the test time, we just perform the test on this graph, and based on their node class labels. Okay. So as a summary, right, for the transactive setting, so they are performed on the same graph. The data sets basically just consist of one graph. The entire graph can be observed in all the data splits. We only split the labels, right? So this setting is basically can be applied to the node and edge prediction task. And for the inductive setting, the training, validation, and test are on the different graphs, right? The data set basically, after we split the data set, we have multiple graphs. So each split can only observe the graphs within that specific split. And the successful model should be easily generalized to the unseen graphs. So this kind of setting can also be applied to the graph task. Okay. So let's take a node classification as example, right? So for the transactive node classification, right, all the split can observe the entire graph structure, but can only observe the neighbors of their respective labels, right? And for the inductive node classification, we have 3 different graphs, right? So each split contains an independent graph and their class labels. And while for the graph classification, we can see that only the inductive setting is well defined for the graph classification, right? Because we have to test on some unseen graphs. So naturally we have this kind of split, right? Suppose we have data set of 5 graphs. So each split will contain an independent graph, right? So this is essentially an inductive setting. Okay, and then the most tricky part is for the link prediction problem, right? So we can recall that the goal of the link prediction is that we want to predict the missing edges, right? But setting up the link prediction problem is a little bit tricky because the link prediction can be considered as a kind of the unsupervised or the self-supervised task, right? So we need to create the labels and the data set by ourselves. So more concretely, we need to hide some edges from the GNN and then let the GNN model to predict whether these edges exist, right? So for example, this is the original graph. So when we validate the link prediction, we probably need to hide these 2 orange edges, right? So then the remaining part will be fed into a GNN model for the training, right? And then when we do the test, we just consider these 2 edges, right? Consider these 2 held out edges and then make predictions. Okay. So more specifically for the link prediction problem that we will split the edges twice, right? So the first step is that we will assign 2 different type of edges in the original graph. Okay. So we have the message updates. We have the so-called message edges. Message edges basically are only used for the GNN message passing or message training, GNN training, right? And for the supervision edges, these 2 orange edges, they are only used to compute the objective, right? So in the other words, that we only perform the message passing on the black edges, right? And after we get the embeddings, we use these 2 green edges to compute the loss function, okay? So after this step, that only the message edges will remain in the graph, right? So the supervision edges are used as the supervision signal for the edge prediction made by the model. So they are not fed into as input to the GNN model. And then we also have the second step split. So here that we need to split the edges into the training, validation, and the test set, right? So still for the option one, we can perform the inductive link prediction split, right? So remember that for the inductive split, we have a data set of three different graphs, right? So each inductive split will contain an independent graph, right? So for example, we can see that we have a training set, validation set, and test set. For each set, it will have two type of edges, the message edges and the supervision edges, right? So supervision edges are not as input to the GM module, right? So for example, for the training set, we use these message edges to train the to perform the message passing and use the supervision edges to do the to compute the loss function. Similarly for the validation test set. And for the option two, that we can also perform the transductive link prediction split. So this is a default setting when people talk about the link prediction problem. Suppose we have a data set of one big graph, right, like this, right? So by definition of the transductive, it means that the entire graph is observed in all the data set split. Because since edges are both part of the graph structure and the supervision, so we need to hold out the validation and test set, right? So to train the training set, we further need to hold out the supervision edges for the training set, okay? So more specifically, we can see that we first need to split the old edges into the training, validation, and the test set, right? And then in the training set, we also have some additional supervision edges. So this is an example, right? So we can see that um, these red edges are used to train, are used for the message passing, right? And then we use the dashed orange edges to compute the loss function. So this is the training time, right? And at the validation time, we consider that this dashed edges is also available. Okay, so we consider that this solid edges as the we use these edges to predict the validation edges. Right? Basically, it means that all the previously hold out edges will become available in the validation set. And similarly, in the test time, that these held out edges 4 to 5 will also become available, and then we just predict the test edges. Right? So as a summary, that um, as a summary, we can actually have four different splits, right? We have the training, training message passing edges, training supervision edges, and the validation edges, and the test edges, right? So the rationale here is that after the training procedure, the supervision edges are known to the GM module, right? So therefore, that the ideal GM module should use the supervision edges in the message passing and the validation time, right? Similarly, that the holdout validation edges will also become available to the message passing in the test time. Okay, so in the other words, that you can consider that the graph actually evolves over time. When some edges become available, it is first used to compute the loss function, right? And later on, it is also used to compute the to do the message passing, right? Okay, so as a summary, that we can see that this is the general training pipeline for the GM module, right? We talk about how can we design the message function, aggregation function, right? How can we stack multiple GM layers, right? And also how can we design loss function, and how can we design the prediction head, and how can we do the training, and also we talk about the evaluation metrics, and at last, we also talk about how can we do the data split to facilitate the training. Okay, okay. So I think that's all I want to talk about in this tutorial. We still have around 10 minutes. Yeah, I will be happy to take any questions. Thank you. Any questions?